So welcome everyone, and thank you for joining us for this morning's webinar. I am Carla Suter from the BC Dairy Association, and I'll be hosting today's session. This is the second of two webinars focused on adaptation in the dairy sector that we are presenting in partnership with the BC Agricultural Climate Adaptation Research Network, Agriculture and Agri-Food Canada's Agassiz Research and Development Centre, and the BC Food Web. The sessions feature an excellent lineup of speakers, and if you missed the first one, you can still watch the recording. The link to that recording is available in the chat. As we begin, I would like to acknowledge that I am hosting this session today from the ancestral and unceded territory of the Stolo Nation. We have people joining us from many places today, and I would like to acknowledge the traditional caretakers of those lands as well. Just a little bit of Zoom housekeeping. Today's session includes two presenters, and we will have a Q&A break after each presenter. We have a couple of additional special guests who will be available to answer your questions as well. Before we get going, I just want to go over a few more things. To ask questions, please use the Q&A box instead of the chat. You will find the Q&A box tab at the bottom of your Zoom control panel. So we'll be looking there for question and answers, not through the chat function. Using the Q&A box will allow you to enter your questions as you think of them and allows us to keep track of them more easily. You can also upvote others' questions by clicking on the thumbs up symbol. We will ask the questions with the highest number of votes first. We also encourage you to say hello to the speakers and your fellow attendees by introducing yourself in the chat box. So it's my pleasure to begin the session with Dr. Victor Lowe. Dr. Lowe is a professor emeritus at UBC's Department of Civil Engineering. Dr. Lowe has over 40 years of experience in biological process applications for waste treatment and resource recovery. He is the principal investigator and co-inventor of the microwave-enhanced advanced oxidation process, the patented microwave peroxide technology for treatment of organic slurries, such as sewage sludge, food, and agricultural wastes that he will be sharing today. Welcome, Dr. Lowe.
Morning, everyone. Can you hear me? You can, right? Okay, good. Okay, let me quickly start with my presentation. The title here is called Integrated Dairy Manure Management System. This is the project that we've been working on for actually quite a few years now. The present one is funded by the provincially significant project from BC Ministry of Agriculture. And my co-researcher is Dr. Mavanik, who is unable to attend today because of other tasks. But anyway, I'll give a very quick presentation. First of all, it's a sort of quick summary about the challenges, opportunities for the livestock industry, because we all have limited land base and in intensive farming. So you see a lot of farms are getting much, much bigger. But the problem then is there are limited land base, you have excess manure applied on land, we have excess nutrient buildup in soil. This potentially cause problem for nutrients in the surface runoff, also groundwater contamination. So one way to do this is resource recovery, okay? Now, if you're looking at BC, there are probably over 80,000 dairy cows in BC, and those producing a lot of manure every year. And they have large quantities of carbon, nitrogen, phosphorus. So potentially this is a good resource for recovery. Traditionally, we look at the waste as something you just try to dispose of. But now I think the thinking is really how do you actually better utilize them? Okay, so land disposal, if you look at the amount of land required for disposal, and in this case, particularly you're talking about the amount that you can apply. Now, if you want to do a sustainable way, the amount applied ideally should be, about in the range of whatever the plant uptake depends on the crop. So I'm using only corn production here, let's say roughly for land in roughly 100 dairy cows. So this is fairly typical BC herd size, about 120, right? So if you use nitrogen as the base, you need about 62.5 acres. If you use phosphorus uptake, you need 133 acres for that herd size of 100. So, and also the regulation regarding P restriction is actually getting much more stringent. So we need to really have a serious look at it. Okay. Now, so what is microwave enhanced advanced oxidation process? This basically is you use a combination of microwave and hydrogen peroxide, a small amount of dosages, and this would actually allow you to oxidize a lot of waste material that you're dealing with. And the reason this thing can work so well is because the combination of microwave and hydrogen peroxide produces what you call the hydroxyl radical. This is not the ordinary hydroxyl iron. Okay, this is hydroxyl radical. This is probably the second most potent oxidant known to man, okay, next to fluorine. Okay, so this is a process that we've developed, in a way by accident, not by our special insight, but we bump into this thing. Okay. Now, so just a quick summary of showing that the electromagnetic spectrum microwave is really only in this range, 3 gigahertz to 300 gigahertz. Right? So even like our microwave oven, your cell phone, those kind of things within that range. Okay. So we're using a limited range. Now, these are the significant factors because if you're looking at how do you operate this particular treatment system, basically is the temperature, the hydrogen peroxide dosages, microwave intensity, and also heating time. So you target a certain temperature range, and with certain amount of force, you like to use as little hydrogen peroxide as possible. And so the exposure heating time usually takes somewhere between 10 to 20 minutes. That's actually very, very fast, okay? So the benefits here is basically, first thing is solids reduction. So this thing breaks up a lot of larger solid particles into finer particles. At the same time, it does nutrient release, allows the nutrients to be released into the solution, which allows you to actually do the recovery. Now, one thing very essential here is the conversion from the longer chain, larger molecules into short chain fatty acid, the VFAs. And so this becomes ideal for the subsequent anaerobic digestion. And this allows you to actually design the anaerobic digester with a much smaller reactor volume. Also, make the biogas production much, much more efficient. I'll get into a little bit detail there, even though I won't get into a lot of the technical results, okay? Now, this is a sort of quick summary of what you do. This one is actually a closed loop, 5 kilowatts, sort of our second generation unit. On the left-hand side here, what you see is the microwave generator. It comes out, we need to have a cooling system. This is the applicator portion, basically for waveguide. And so what comes here is the wave tuner. So it allows you to optimize the process. So the feed material comes in from here with the pump, and it goes up from here and then goes to the reservoir. And now because it's only 5 kilowatts, so for each pass, when the thing, let's say dairy manure goes up from here up to here, it only raises about 20 degrees centigrade, and we don't have a preheating here. So we have to go four to 5 cycles in order to reach, say, 90 or 100 degrees centigrade for treatment. So this is a closed loop system. And then, so when the temperature reaches a certain level, say roughly above 60, maybe about 80 degrees centigrade, you start adding hydrogen peroxide and you see the treatment results, okay? This one is a newer generation, is actually at Agassiz. This is the basically the microwave generator. And here is the waveguide comes out. Here is the newly designed 4-pass applicator. And again, so the thing passes on basically four passes to maximize the heating, the heating efficiency. Okay. The advantage of the system here is you actually have a relatively small footprint. The whole microwave system actually can easily be housed in a 20-foot standard shipping container. And so the design is relatively simple and easy to operate. You can actually do them on modular form. So if you want to expand, you could just stack them up, or, so it doesn't take a lot of footprints. It's easy to be retrofitted into existing facility. Temperature-wise, it's actually, compared to other technologies, we're actually in a much lower range, 90 to 120 degrees centigrade. Short heating time, 10 to 20 minutes. Energy efficiency is very, very high. There's a low operational and maintenance cost. Okay. So this is a sort of general diagram. If you have liquid dairy manure, now on every dairy farm, you have liquid solid separator. So we're actually tackling only a small portion. Sorry, how come this thing jumps? This is the, so if you have a liquid fraction of dairy manure comes to microwave treatment system, basically it does solids reduction. And this also allows you to do, because the solubilization, you could possibly recover nutrients, phosphorus and magnesium, ammonium phosphate in the form of struvite. You could also do biogas anaerobic production through anaerobic digesters. So the output here is you have a high N and P recovery. You also have a much better biogas production. Okay, so what's in the integrated treatment system? The key components here is obviously the microwave system. Then what you add on is the struvite crystallizer, and you can also use, well, the reason we use here advanced anaerobic digesters, because you are no longer using the conventional system. If you look at the conventional anaerobic digesters, when they do the things on farm, you're looking at about 40, at least 40 days hydraulic retention time, or even much longer. I used to do a lot of those things many, many years back, but I'm super excited because we can now do it for actually less than 8 days, somewhere between 5 to 8 days. So this is a general diagram. This light blue thing is the existing farm. You have milking powder, you have barns, and you do manure holding pits, liquid solid separator. Now we're basically doing only the liquid storage portion because the solids portion goes somewhere else. And also not all the phosphorus nutrients needs to be recovered, because a lot of things can be reused on farm. So what we're saying here is the option here is you put a microwave system here. And if you want to do struvite recovery, you basically go this route. If you want to do biogas, the thing is actually now gaining a lot of interest, because the Fortis BC is actually aggressively promoting renewable biogas, and the price actually has gone up quite a lot. And so this option is very, very good. But if you use a conventional system, it's going to cost you a lot, right? So this is sort of a general diagram, allows you to do electricity, or if you want to do heat, okay? This is the system that we have at UBC Dairy Farm. This is actually right behind this building. Is what the tall building here is actually the one that they actually handle manure storage and liquid solid separation. Okay, so we tap into that. This is the one that houses the microwave unit. This is the one that we do the struvite recovery. This is the sort of upflow kind of a fluidized bed system. This is a closer look at the struvite recovery. This is one of the pilot scales that we are using. The struvite crystal actually is in this shape. It's a slow release fertilizer. So, and this thing actually can be very, very valuable. The price is probably something like $1,500 a ton. So if you look at anaerobic digester, because of the microwave pretreatment, so this thing now allows a lot of VFA to be available. So you can do a much, much faster organic loading. You can have a much higher biogas production. So this potentially provides the renewable biogas income. The advantage here is you have a much shorter hydraulic retention time. Usually this hydraulic retention time is less than 8 days. Actually, our recent study shows that we could easily do it on 5 days, which is, is really, really good, which also means you actually now have a much lower capital cost if you're building a new anaerobic digester. So we're looking about the 3 R's, and we're looking about the bioenergy reduction, you call it nutrient recovery, also reduce carbon footprints. I believe that UBC actually is looking at potential carbon credit. I'm not an expert in that area, but apparently this thing potentially could be very profitable too. Okay. Now, so the overall benefits, you have a reduced amount of nutrient supply on land, and that's a major concern. You also have reduced water pollution, both surface and groundwater. Future market potential for phosphorus fertilizer, because the thing is a slow release thing. And actually, on top of that, we have also developed a newer technology that produces not only struvite, but also K-struvite. Because if you look at struvite, it's magnesium, ammonium, phosphorus, it does not have the potassium. But particularly for dairy waste, because they're rich in all kinds of cations, we can actually do K-struvite. So we've done actually three demonstrations. The first one is at the James Wastewater Treatment Plant, Abbotsford. That one is already completed. Presently, we're doing this work at the UBC Dairy Center. Also, there's a similar system going on at the Metro Vancouver. And so if you look at the design criteria, if we use the typical herd size, 120 lactating cows, and you do only the liquid portion, we are looking at both the volume of liquid manure fraction is about this much plus minus 20%. Total solids is roughly 4%, microwave operation, let's say roughly 8 hours a day. And this is the cost figure. I'm not particularly comfortable about this. This is done by WSP for UBC on a special contract. The number is probably not quite as accurate because this was done in 2018. And now with the potential renewable biogas commanding a much better price, the number should look actually a little better than this. Okay. But you're looking at about, if you have 120 cows per size, close to $2 million capital cost, which is actually not bad compared to if you want to do anaerobic digestion. There was a workshop many years back. A lot of consulting firms went, and the minimum is like $2.53 million. That basically turned everybody away, right? So this is a sort of quick number. And so if you go from different herd sizes from 300 to 3,000, you're looking about the annual potential revenues. And so this profit is roughly $350 per cow. It's not too bad. Actually, this number should be actually higher now with a better price. I think that's pretty much summarized what I wanted to say. And I have actually a few more things later if there are questions. This project is supported by provincially significant project program, BC Ministry of Agriculture. Also, WSP, formerly OPUS, actually being very, very supportive. And also we appreciate the collaboration from UBC Dairy Center. Thank you. Am I over 20 minutes?
No, you were under. We're perfect. It's great.
All right. No.
So we will now answer questions from the audience. If you haven't already, please take a moment to type your questions into the Q&A box. We do have one, so while folks are typing their other questions.
How do I get off my screen to look at it? So I need to get off my PowerPoint, right?
I'll be reading them out loud, but you can also take off your PowerPoint, whichever you prefer. So the first question is the microwave and H2O2 treatment of manure releasing other than methane, greenhouse gases, or other pollutants into the atmosphere a serious issue?
No. Actually, what we're using is the beauty about hydrogen peroxide is only hydrogen and oxygen, right? And we're using a very, very small amount of this. So when this actually is used up, we make sure there's no hydrogen peroxide residue in the final treated thing. So there's really not much released. The only thing is because the dairy manure is a very, very complex material, it has a lot of other cations. So in order to do recovery for struvite, in order to access that P phosphorus, you will need to actually you need to use oxalic acid to knock out a lot of calcium first before you can get the phosphorus. There's no other things released.
Great, thank you. And if anyone else has a question, please feel free to enter it into the Q&A box. There's a lot to think about in that. So I think folks are putting together their thought processes to put some questions together. Thank you so much, Dr. Lowe. I really appreciate that.
You're welcome.
Very informative session. Please continue to put your questions into the Q&A box. And I will shortly introduce our next presenter. If you think of something later on for Dr. Lowe, please. Oh, here we go. What would the volume of the struvite be from an average herd?
This actually is something I thought about. Well, the whole thing depends on how much you want to recover, because when you do a manure management on the farm, what you want to take out is the excess portion, because every farm takes in fertilizer. They also grow their own crops, but the problem is everybody wants to make sure they got good crops, so you apply a lot of fertilizer. So what you need to do is to take away only the certain portion. So it's kind of a flexible, depends on, you need to do a sort of more thorough analysis for each farm, and depends on, do a nutrient balance and see what's available, how much you need to remove in order to be sustainable. So there's not a sort of one answer for all the farms, right?
For sure. Great, thank you. And now we have another. Do you see the cost as being the biggest barrier to operations putting in this type of technology? Or what other barriers to implementation do you see at this point?
I think cost is always a problem. Now, I've been doing agricultural waste management for many years, and I think usually the number one problem is waste management usually is a low priority, because it does not generate a lot of cash for you, right? And so it's always at the very end. Everybody wants better milk production, they want animal health, everything. And so it's almost the last one they want to address. So cost always is a problem. Now, in this case, we have reduced the cost a lot. Now, there is one potential difficulty here is I think every farm operator wants to dedicate their energy for milk production to make money. And so if they need to learn how to use the system, that's one potential problem. So what we're looking at is somehow make the thing pretty much turnkey, automated. So that's one additional barrier we need to overcome at this point, but that's not difficult. Yeah.
Great,
I'm not sure whether that answered the question.
Great. Well, thank you so much, Dr. Lowe. That was very informative. And I think it's another great solution to a major problem we see on dairies currently in BC. Thank you so much, Dr. Lowe. So if there are any further questions, please continue to type them into the Q&A box, and Dr. Lowe can perhaps type in his answers, and we may have time for them afterwards.
Okay. Yeah.
So I'd now like to introduce Dr. Aime Messiga. Dr. Messiga is a research scientist at Agriculture and Agri-Food Canada's Ag Seed Research and Development Centre. His research program focuses on soil and nutrient management. His current projects aim at improving our understanding of nutrient cycling and dynamics. He is collaborating with colleagues across Canada and local industry to improve starter fertilizer P recommendations in silage corn systems and to adapt an agri-environmental indicator of the risk of P transfer from fields to water sources. Welcome, Dr. Messiga. You'll want to unmute yourself. Sorry, Doctor.
Okay, thank you, Gala, and good morning to everyone. Can you hear me now? Okay, so yeah, I want to take this opportunity to discuss some aspect of my research. And I want to start the meeting by discussing the place of phosphorus management in the new BC Agricultural and Environmental Management Code of Practice. The code was launched in February 2019, and it applies to all agricultural operations in BC. There are 3 points in the code of interest as it's applied to phosphorus management. So point 53, 55, and 57. I want to discuss a little bit this point and share how we can actually improve the new version of the code that will be released in the years to come. So, okay, point 53, when we go through the code, point 53 states that a phosphorus test must be conducted at least every 3 years. And when we look at point 55, it states that the test has to be performed using the Kelowna method. And point 57 states that the goal to prepare a nutrient management plan is to minimize the risk of phosphorus and of nitrogen and phosphorus loss from a field to the environment. But as we can see, these points need to be further developed and expanded. For example, we need some specific information on phosphorus management practices that would ensure the drawdown of soil phosphorus after 3 years. We also need some environmental risk indicators to predict the risk of phosphorus loss to the environment. In fact, there are gaps in these codes that need to be filled as it pertains to phosphorus management. Now, I want to briefly discuss about phosphorus in silage corn in the plant itself. What we know is the concentration of phosphorus in silage corn on most plants vary between 0.1 and 0.5%. And if we consider silage corn yield, annual silage corn yield varying between 15 and 27 tons per hectare, it means the average P uptake would also range between 45 kilogram and 60 kilogram P per hectare. So that is the amount of P that is annually taken up by silage corn in 1 hectare of land, 45 to 60 kilogram P per hectare. At any given stage of silage corn growth, if the concentrations of P, or phosphorus in the plant, fall below these ranges, deficiency symptoms will appear on the plant. And these symptoms could vary from an entire plant turning into a purple color, or the margin of the leaves turning to purple. And the worst case scenario would be stunted plants, which would affect the final yield of silage corn. To avoid these deficiencies on plant, and particularly young plant, farmers in BC and most producing silage corn areas use starter fertilizer blends. And our farmers in the valley are familiar to some blends. For example, the 1152-0 blend, the 944 blend, the 23-25-0 blend. These are granular fertilizers. And we also have the 10-34-0 blend, which is actually a liquid. The main characteristics with these four blends is they are high in phosphorus content. So at this point of the presentation, I think it would be important to talk about starter fertilizer. What is actually a starter fertilizer? It is a small amount of fertilizer placed 2 inches near the seed and 2 inches below the seed. So 2 inches near the seed and 2 inches below the seed. At this distance, most salt present in the blend will not affect the germination of the seed. And in addition, phosphorus fixation is reduced because the contact between the fertilizer and the soil is limited. So phosphate anion will be kind of free in the soil solution. Also, starter fertilizer would then support the growth of young plant until the development of root. Starter fertilizer is particularly important in areas where low soil phosphorus prevail, low soil temperatures prevail, particularly early in the growing season. I want to discuss a little bit the growth stage of a corn plant. It starts at emergence up to R6 or maturity. So emergence, they are actually, the plantlet actually doesn't have any root. So it relies more on phosphorus and nutrient present in the seed. At V1, which corresponds to the growth of the first leaf, the root of the plantlet, the root system is still very shallow, very small. So at this stage, V1 or one leaf stage, the plant doesn't have enough root to explore a big volume of soil in order to take up phosphorus. So the plant will still rely slightly on nutrient and phosphorus in the seed, but also in the phosphorus that is free in the soil solution. Now, from one leaf stage to V6, which is 6 leaf stage, the root system starts to develop. And it is at this period or this growth stage that starter phosphorus is actually important, because within these growth stages, the root system is not yet developed for the plant to take up P or phosphorus from the soil. So starter phosphorus is needed. But after the V6 stage, as you can observe, the root system starts to be well developed, fully developed. Now, the plant can rely on phosphorus from the soil. And as we know, our soils in the valley are rich in phosphorus. So the plant does not need phosphorus from starter fertilizer, because now the root system is well developed to allow the plant to take up phosphorus from the soil. Then a best management practice as it relates to phosphorus management is to determine and apply the amount of starter phosphorus that is needed during this critical period from emergence to the 6-leaf stage. And that has been our goal during the past few years. I want to present now some background of phosphorus management as it relates in the valley, in BC. First, as we show in previous slide, phosphorus removal for silage corn vary between 45 and 60 kilograms of phosphorus per hectare. Currently in BC, farmers apply up to 90 kilograms of phosphorus per hectare, including 50 kilograms of phosphorus per hectare as manure and between 25 to 40 kilograms of phosphorus as starter fertilizers. Some of our previous results allows us to say the cumulative phosphorus budget, which is the difference between phosphorus input and phosphorus removal, is linearly related to the concentration of phosphorus in the soil. What does that mean? It means if the P budget is in excess, there will be buildup of phosphorus in the soil. So what we also know is at this stage, excess of phosphorus will continue to increase in our soils in BC if we don't take any steps, and that will also increase the risk of phosphorus contamination in water sources. That is the state of phosphorus management in BC at present. So what can we do? In the past years, as I mentioned, we are conducting trials in farmer setting as well as at Agassiz Research and Development Center. So far, we have been going through two phases. The first phase spanned between 2018 and 2019, where we ran 11 silage corn in farmer settings. So I want to give some background of the first stage. It is particular because this first stage wasn't familiar to farmers. So they didn't quite get what we were doing when we were discussing. Actually, in this first stage phase, we work more on the structure of our treatment. So starter fertilizer phosphorus was applied at seeding, at planting, and manure was applied at 6-leaf stage. And this was done because we wanted to separate the effect of starter phosphorus and the effect of manure phosphorus. As we mentioned in our growth stage graph, starter phosphorus is needed mainly between emergence and V6 stage. So that's why we apply starter phosphorus at seeding and follow the growth of plant up to V6 stage. Then at V6 stage, we side dressed manure to follow now the growth until harvest, maturity. So this is not the standard practice used by farmers in the valley. But what we did, we started with 5 rates of starter phosphorus, going from 0, 5, 10, 15, and 20. And we side dressed the remaining phosphorus for a total of 35 kilograms at V6 as manure. And we also apply nitrogen source as urea. Now, what are some of the results we obtained? In 2018, what we show in most of our site is we had a response of young silage corn plant at V3 and V6 to starter fertilizer phosphorus. But what we can also see is the response was a linear plateau, or described by a linear plateau model, which means silage corn, the dry weight of silage corn increases with increasing starter phosphorus rate up to a critical rate, which was around 7.5 kilogram of phosphorus per hectare. So in most of the site. So then what we can say is, so far, in 2018, the critical starter phosphorus rate was 7.5, but let's say up to a maximum of 10 kilogram of phosphorus per hectare, which represent a reduction or a cut of up to 75% when we look at the present application rate. In 2019, we had 8 silage corn trials in the valley, but we didn't see any effect of starter phosphorus fertilizer across the 8 sites, from the 3-leaf stage to the 6-leaf stage. What are some of the reasons? So we went to look at the evolution of soil temperatures during the early growing season, May to June, which correspond to the period between planting and the sixth leaf stage. What we observe is in 2018, soil temperatures were colder, right? And during a long period, during a long period compared to 2019. So it looks like because the soil temperatures were low, colder, so the soil wasn't able to release phosphorus to the young plant. So the young plant had to rely more on starter phosphorus that we apply. While in 2019, where we had high temperatures during that period of the growing season, the plant took part of their P, the young plant took part of their P from the soil. Now, when we look at the yield in 2000 at harvest in 2018 and 2019, there was no effect of starter phosphorus and manure on final yield on harvest. That means the effect we saw in 2018 didn't carry through harvest. Now, I want to discuss a little bit about the second phase of our trials. This second phase span from 2020, last year, and this year. So our plan is to have around 8 to 10 silage corn trial. And now that we were able to define the critical starter phosphorus rate for silage corn. Now it was time to use the standard practice used by farmers in the valley. That means we allow farmers to apply manure in our plots as they would do in their field. Then at planting, we apply starter P, our 5 rates of starter P, 0, 5, 10, 15, and 20 kilogram P per hectare. In this way, we were sure now to do exactly what farmers will do. And we sample the plant at 3, 6 leaf stage and harvest. So results of last year are consistent with what we found in the first period. There was no to little effect of starter phosphorus, and the critical rate for the few sites where we saw some response, for example, here was basically around 10 kilogram of P of phosphorus per hectare. There is one aspect of this study we were struggle with. Even though we were able to define a critical starter phosphorus rate of 10 kilogram per hectare, we still observe some deficiency symptoms in young plants. So in our discussion with our collaborators, TerraLink and Energetic Canada, we found that many farmers in the valley use some biostimulant, and they seem to be happy with the effect of the biostimulant. We then agreed to conduct some demonstration trials in farmers' fields. The goal was to compare a low starter fertilizer phosphorus blend, 20-10-0, mixed with a biostimulant. So we went with a low starter fertilizer phosphorus blend, 20-10-0, mixed with a biostimulant. And to compare this mixed with some high starter fertilizer blend. So we had 5 treatments in 9 demonstration trials. So these trials were not repeated or blocked. So there were only strips of corn with this treatment. So we had a control, no phosphorus. And we had a high starter phosphorus blend, familiar to what farmers will use, 23-25-0. A low starter phosphorus blend, 20-10-0, mixed with biostimulant. This was our treatment of interest. A low starter phosphorus blend alone, 2010 without the biostimulant, and a treatment which only included biostimulant mixed with urea. So how the result look like? So if we focus on our treatment of interest, the low starter phosphorus blend 2010 mixed with the biostimulant, what we observe in most of, when we put together all the farms, in 2019, we had around, I think, 5 sites. So when we average the treatment value in over the 5 sites, we found that in 2019, our low starter phosphorus blend mixed with biostimulant had a beta growth at the 3-leaf stage, as well as in 2019, in 2020, and also at 6-leaf stage in 2020. And the young plant look healthier, look more stronger compared to the older treatment. So what it means we here have an option of using a low starter fertilizer blend with biostimulant in order to have a plants that look healthy without deficiency symptoms. But as I mentioned, these trials were not replicated. So we need some trials or experiment with repetition to make sure the effect we are observing are significantly or statistically significant. So what is the take-home message of this presentation? First of all, critical starter fertilizer phosphorus should vary between 7.5 and a maximum of 10 kilogram P per hectare. And so far, the knowledge we are also developing is by mixing a low starter fertilizer phosphorus with biostimulant, we will reduce the incidence of deficiency symptoms on young silage corn plants. And these results could be considered as entry point for phosphorus management in the BC Agricultural Environmental Management Code of Practice Code for silage corn. And we need additional trials in this site with a wide range of crops we grow in the valley in order to feed this code. As for 2021, we are looking for farmer sites and place. If some farmers are interested, feel free to reach out to us. And I want to conclude this presentation with another aspect of our research, which is the development of a phosphorus saturation index for BC soils. So far in Canadian agro ecosystem in the East, Quebec and the Maritime, Ontario, Alberta, Manitoba in the prairie, so they have phosphorus saturation index they use to monitor the risk of phosphorus loss from field to the environment. In BC, we are developing a phosphorus saturation index, or PSI, for the acidic soil of the valley. And we've published some data. The papers are available, and the goal would be to extend this approach to the calcareous soils of the Okanagan Valley. So there's still some work to do, and we hope by the time we will complete, we will have enough input to feed the new BC Agricultural Environmental Management Practice Code. So then I would like to acknowledge the effort of my research team, my technicians, and the many graduate and undergraduate students who support this work. And I also want to acknowledge the collaboration of UBC, TerraLink, Energetic Canada, the BC Dairy Associations, and the many local farmers who have been so gentle to allow us to drive in their field so many times during the growing season. So I want to thank you, and please feel free to ask your question. Thank you.
Thank you so much, Dr. Messiga. That was really incredible. Thank you. We do have a couple of questions already in the Q&A box, so go ahead and ask more if you have them while Dr. Messiga answers the ones we already have. So someone was wanting just to check if the critical start fertilizer P rate was in total phosphorus kilograms per hectare or P205
P,
kg.
yeah, P per hectare, not P205 kg.
Okay, thank you. Now, examining the 2019 results, you looked at 2018 temperatures. What about your 2017 results? Did you also look into the 2016 temperatures?
Yeah, that is a good question. Unfortunately, we only started this trial in 2018. Right. Yeah, because I started working at Agassiz in May 2016, and by the time we developed the program and get some funding, so it was already 2018. So we don't have results from 2017 and 16.
Great. Okay, thank you. But I'm sure this year you'll be able to compare to your previous findings.
Yes.
Building on what we already have. Thank you. Could you comment a bit more on the soils of the trial sites? What kind of textures were represented and what were the pre-existing soil phosphorus levels?
Yeah, good question. So in 2018, in 2018, we had phosphorus content going from somewhere around 60, 70 ppm of meliche to almost 200 ppm of meliche 3, right? And the soils where we had some loam and silty and sandy loam soils. So yeah. So in 2018, the site were mainly located in the Agassiz and Rosedale region. And in 2019, we moved a little bit further to Agassiz, to Chilliwack. 2018 and 20, we were in Chilliwack, and we had one site in the Okanagan.
Great, so lots of variety. Great, thank you. In the previous webinar, Dr. Bittman discussed the use of solid portion of dairy manure as a substitution of starter phosphorus fertilizer for silage corn. Can you comment on that and maybe provide other potential organic and or farm generated phosphorus sources?
Yeah, I think Dr. Bittman had a lot of experience in this work, and I think he was very clear in his presentation on the option of using solid dairy. The solid portion of manure was well developed. So I really don't know what I will add on this.
Okay, thank you.
Mm-hmm.
Given that the industry standard is not to apply manure post-planting, do you anticipate that there would be an equipment barrier for growers to side dress with manure at the 6-leaf stage?
Yeah, that is a good question. We have many barriers, not only the equipment, but the size of our land, right? So as I mentioned, the purpose of the first phase was to make sure we separate the confounding effect between the effect of starter fertilizer and manure and P from manure. That is why we opted with that first phase to separate, to make sure the effect we are observing in terms of starter fertilizer were mainly only starter fertilizer. That's why we first apply starter fertilizer, then apply manure. In the second phase, we are actually applying manure, then plowing the soil before now applying starter fertilizer at planting, which is the conventional or the standard practice used by farmer. It will be challenging to apply manure at side dress given the size of our land. In Ontario, in Quebec, yes, some part of the US where they have huge land, they are able to do this easily.
Right. Great, thank you. If there are further questions, please continue to pop them into the Q&A box. We'll just wait a few more moments in case anyone has any further questions, but thank you very much for those, Dr. Messiga.
Mhm.
Oh, okay. Given that no effect of starter phosphorus on harvest yield, should starter P be applied in the first place?
It would depend on the level of risk farmers are willing to take. Because honestly, when you look at the young plant in the control plot early in the growing season, they don't look quite healthy or robust. So farmers might be afraid to take the risk or willing to look at their plant at this stage and still be confident that at harvest they will get enough silage corn for their livestock. But normally, what our data are showing is without starter P, plants can rely on manure P that is applied. But it depends on the level of risk, and it also depends on the temperature, right? So it's that which is difficult to predict.
Of course. Yeah. Great, thank you. Can you speak a bit more about biostimulants? I know more trial work is to come, but what is the mode of action with these products that might be impacting phosphorus uptake in such a meaningful way?
Yeah, both biostimulants are a kind of cocktail of microorganisms, right? Where you have some bacteria, you have some fungi, including some strains of mycorrhizae. The idea is they kind of solubilize the phosphorus even at this low soil temperature. So they make phosphorus in this in the soil available, and the young plant can take up the phosphorus. And there is another aspect of the biostimulant also developed by Penergetic, but we haven't studied that one. In fact, that biostimulant, Penergetic J, kind of help to solubilize the phosphorus that is present in manure and make it available. But I can't really develop on that because we haven't studied that aspect. But the main mechanisms is the microorganisms present in the biostimulant cocktail will solubilize the phosphorus that is attached to the soil particles and make that phosphorus available to the young plant. And this work even at low soil temperature.
Excellent, thank you. Well, that looks like it wraps up our questions for now. Thank you so much again to yourself, Dr. Messiga, and Dr. Lowe for presenting for us today. We will be sending out a copy of the recording of today's session. And if you missed Monday's session, you can watch the webinar on the BC Agricultural Climate Adaptation Research Network's YouTube channel. That link will be available in the chat. Thanks again to all of our partners in today's session. If you have any feedback on today's webinar or suggestions for future sessions, please tell us. You'll be directed to a 2-question survey after the session ends. We really appreciate your feedback. Thanks so much again to our 2 great presenters today. Thanks to everyone who joined us, and we hope to see you again soon.